imaging. Basically, he works on image processing through wavelets. Sir has more than 9 years of teaching experience, and in this duration, he has published more than 20 papers. He has guided 6 students. 6 students have awarded under his guidance, PhD award under his guidance, and 4 students currently pursuing PhD under him. So I would like, on behalf of the organizing committee, I would like to invite sir to begin his talk.
Hello. 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 Am I audible? Okay. Am I audible now? Okay. Thank you, Chandrali madam, for introducing me for this gathering. I am very much thankful to the organizers for giving me an opportunity to present one of my contributions in this conference. Okay. So I used to work on wavelets and develop techniques for solving differential equations, maybe ODR, PDR system of differential equations. Okay. Parallelly, then I will do analysis related to real analysis. Okay, good. So this is the, everybody can understand this one. And let me share one story behind this one. And I am very much sentiment about Tumkur University conferences. Because in 2017, I don't know exact year, either 16 or 17, I presented one talk by you don't know a function, just you know function, means you know the function, but the task is to, it has how many derivatives? It has how many derivatives? By looking at geometry, we can check that it is continuous or not. If you draw the function without lifting your article, then one can loosely speaking can set that it is continuous or not. What about the derivative? First order derivative. First order derivative, if you draw unique tangent at each point, then it is differentiable. What about second order derivative? What about third and beyond? So then there are some studies or researchers are done to calculate a given function, how many derivatives it is having. We are having analytical expressions by Fourier coefficients. So I presented that one in the 2017. So one of the audience posed me a question without knowing the Fourier coefficients, how to judge that it is continuous or not. But if you know the function, it is an easy job. But if you don't know the just function data, means we are having the sample. How to say that this function is continuous or discontinuous? So that question made me to think and sit, and that is answer today I am presenting. It took how many? Almost 6 years. Okay. Then that finding communicated to 3 to 4 journals. It is continuously rejected. And at the end, so I took the suggestions or comments from the reviewers, and finally it is accepted in the Springer. Okay. So and my selfishness is that I am expecting 1 or 2 questions from the same audience, and I will be delivering that answer in the next forthcoming Tumkur University conference. That is in your hand. Okay. Thank you. So next. Properties of R-valued. My presentation is in containing 5 points, as usual, introduction, sharper bounds of for Har-Wavelet coefficients, resultant discussion, conclusion and future work, as like it will be ending with references. Okay. So Har-Wavelets, just wavelet means many of the, I don't know how many you know the definition of wavelet. Wavelet is just a function, loosely speaking. Wavelet is just a function. How it looks like? It is having compact support over some interval, and beyond some interval it is zero. It is non-zero over small interval. Beyond that one it is zero, and it is having 2 to 3 properties. Its integral is zero, and it is having some multi-resolution analysis properties. Okay. So now, why you have to study wavelets? Okay. What is the behavior of sine function? Behavior of sine function. Is it zero? It is throughout the real line. Throughout the real line, it is not zero. It do not have compact support because R is not a compact support. R is not a compact set under Euclidean topology. Okay. So we need a functions. They are having compact support. They are having compact support. They are nothing but wavelets, and very small compact support is the Har wavelet. Okay. Next slide. This is the phi. It is 1 in the unit interval, and beyond it is 0. This is called father wavelet. Okay. Now, next it is MRF properties. I said this Vj is nothing but nested properties, Har wavelet spaces, and L square 0 1 means set of all square integrable functions on 0 1. It forms a Hilbert space. Okay. Next. Now this nested spaces having the properties that Vj plus 1 can be decomposed into Vj and direct sum of Vj and Wj. Here Wj is nothing but orthogonal complement of Vj in Vj plus 1. This Vj plus 1 is splitted into direct sum of 2 subspaces, and those 2 subspaces are orthogonal. Means what is the meaning of this one? Any element in Vj plus 1 can be decomposed into 2 subspaces. One component is coming from Vj, another component is coming from Wj. These 2 components are orthogonal. Orthogonal means angle between them is pi by 2 or 90 degree. Okay. Next, this is the psi of t. This psi of t is nothing but over the unit interval. First half interval it is 1. In the second half interval it is minus 1. Because it is having, what is the area of this function? What is the area of this function? In the first half interval 1. In the second half interval minus 1. What is the area? What is the area? Area is 0. Now this acts as a wavelet. This acts as a wavelet. Area means you just complete the rectangle. First rectangle is half. The second rectangle falls in the negative x-axis. Minus half plus minus half is going to be the 0. Area is 0. It acts as a wavelet, and this is called Har wavelet. Otherwise it is also called mother wavelet. So just like in the previous slide we saw the father wavelet, and this is a mother wavelet. One can expect what kind of wavelets? Father wavelet, mother wavelet. Next, daughter wavelets. But boys are very unfortunate. We don't have boy wavelets. Okay, not BOY, BOY, BYE wavelets. Boy wavelets or boy wavelets are not there. Only daughter wavelets. Okay, thank you. So this Vj can be decomposed as a orthogonal sum of j subspaces V0, orthogonal sum V0, W0, W1 and Wj minus 1. This means any element. Here we are having previous slide. Okay. This V0 is a subspace spanned by father wavelet, and W0 is a subspace spanned by the mother wavelet. Next, W1 is a subspace spanned by the first generation daughter wavelets. Next, W2 second generation daughter wavelets up to Wj minus 1, J or J minus 1 stage daughter wavelets. Okay. So what is the gain here? So, and those bases are orthogonal bases. We are going to project an arbitrary function orthogonal projection to Vj. Orthogonal projection to Vj. Okay, this orthogonal projection in Vj can be decomposed into components of V0, W0, W1 and etc. So that is represents the equation number 1. So here yes, phi of x is the father wavelet, and in the double summations j equals to 0 to capital J minus 1, and these are the djk psi of 2 power x minus k. This is called the mother wavelet, and this is nothing but s0 0 is nothing but integral over 0 to 1 f of t dt. In an inner product space means this Hilbert space. When do you say that a vector space is Hilbert space? It has to satisfy a complete inner product space is called the Hilbert space. What is the inner product here? Just analogy, what is the dot product in Rn? Given two n tuples, we are going to write dot product in Rn. x1 into y1 plus x2 into y2 plus x3 into y3 and so on plus xn into yn. Whenever the tuples are complex, then we are going to write x1 bar into y1 plus x2 bar into y2 and so on plus xn into yn bar. You can put complex conjugate in the first coordinate or second coordinate, is immaterial. Okay. So how to extend this dot product to the continuous function? This dot product involves a summation. What is the extension of summation? Integration. That is the dot product. Okay. Because of orthonormal basis, these coefficients are very easy to compute. These components are very easy to compute. What is the first S00 previous slide? What is the S00 here? S00, it is nothing but dot product of f of x and phi of x. Dot product means this is the integration. And what is the djk? Because of orthonormal basis, djk is nothing but dot product of f of x and this wavelet. Because of orthonormal basis, this linear combination coefficients appears an easy job to compute because it is an Hilbert space. Okay. So these are the coefficients, and S00 is the coefficients corresponding to father wavelet, and these D00 is the coefficient corresponding to W0, and D10, D11, it's a coefficient corresponding to the space W1 and so on. In each space we will having 2 power j coefficients. Here dj's are called the Haar wavelet coefficients. This djk are called the Haar wavelets coefficients. These coefficients will have information about a function f over the compact support of the wavelet. These coefficients will carry information about the function over the interval compact support of the wavelet. Next slide. Okay. So this is what is the compact support of the wavelet? Here the 0-1 closed interval 0-1 is divided into 2 power j intervals. Means the dyadic subintervals. What are the dyadic subintervals? K by 2 power j, k plus 1 by 2 power j. So these intervals are called dyadic subintervals. So this djk will be 0 in the interval k by 2 power j and the end k plus 1 by 2 power j. As I said, in the k by 2 power j, k plus 1 by 2 power j, in the first half interval 1, in the second half interval minus 1. So I am using that one, and this is f of t, means because this is plus 1, k by 2 power j to midpoint of k by 2 power j, k plus 1 2 power j is nothing but 2k plus 1 divided by 2 power j plus 1. It is half in the first half interval, minus in the second half interval. And this absolute means what is the size of this coefficient? I am interested. What is the size of this coefficient? Means absolute value. Absolute. What is the absolute value of mod djk? One means how much big it is. I am interested to measure how much big it is. And this closeness will intimate me to measure the given function is continuous or not in the subinterval of k by 2 power j, k plus 1 by 2 power j. Okay. So now this how I got second means one of the upper bounds is mod djk is less than or equal to 2 power j by 2 into norm of f. This inequality is from the Cauchy-Schwarz inequality. This inequality is from the Cauchy-Schwarz. What it says, Cauchy-Schwarz inequality? Absolute value of inner product of two functions. Absolute value of inner product of two functions is less than or equal to norm of f into norm of g. In other words, absolute value of inner product of f and g is less than or equal to norm f into norm g. So here f is wavelet and g is nothing but f. Okay, you can interchange one or two, no problem. So this equation 2 is derived from by using Cauchy-Schwarz inequality. It's a very crude upper bound. So we need sharper upper bounds. So what the meaning of sharper upper bounds? Suppose if I ask the following question, how much distance from Bangalore to Tumkur? Suppose a person don't know about this city's distance, then he will guess something, estimate something. Suppose if a person is from Andhra Pradesh somewhere else, he will give the answer 200. The distance between Tumkur and Bangalore is less than or equal to 200. It's a correct answer or wrong answer? Correct answer. But we need sharper bound. So what is the sharper bound? Distance between Tumkur and Bangalore is less than or equals to 85 kilometers. I don't know exactly. Yes? Which one is better? 85 or 200? 85. Just think this is nothing but the 2 power j by 2 into norm of is 200. So now I am interested to find sharper bounds. I am interested to find sharper bounds. Okay. So now how one can obtain the sharper bounds? What is the underlying function? F is continuous on the closed interval 0, 1. I can use all the properties of continuous functions on a compact set. I am going to use those, and there are somebody, they already worked here and there are some bounds, and I want to compare whatever derived bounds and in the existing in the literature. Okay, this is the two thing. I need sharper bounds and I want to compare these bounds with the existing literature. Okay, this is my goal. Okay, good. So next, so what is the existing in the literature? The third equation that is existing in the literature. Who has done Majak? It's not Majak, Kannada Majak. His name is Majak. Okay, good. He Majak has calculated absolute value of R wavelet coefficient is less than or equals to eta divided by 2 power j plus 1. So this eta divided by 2 power j plus 1 is again less than or equals to 2 power j by 2 into norm of f. It is sharper bound compared to the Cauchy-Schwarz inequality. Okay, it is sharper bound compared to Cauchy. So it is somewhat better. Here assumption is that this eta, what is eta in the equation number 3, where eta is nothing but upper bound of the derivative of f. Upper bound of the derivative of f. To compute the third equation, I need the information of the derivative of f. I need the information of the derivative of f. If suppose f is not differentiable, then equation 3 is not useful for me. The equation 3 is not useful for the functions which do not have derivatives. Even though derivatives, but it is unbounded, then the equation 3 is not useful. So now by keeping in this mind, what I have done, suppose a function is not differentiable, then how to derive sharper bounds. Suppose if it is differentiable, then I have to compare my bounds means derived bounds to the existing in the literature. Okay, next slide. Next. Okay, thank you. So how one can reach the same goal? Here definition I am using is oscillation of a function. Oscillation of a function. What is the oscillation of a function? So definition, the oscillation of a bounded function. Here I am not using any kind of derivatives, nothing, just bounded function. Okay, good. The oscillation of a bounded function f on closed interval ab is the supremum of the set difference between absolute difference between f of t1 and f of t2, where t1 and t2 belongs to the closed interval ab. Okay, of numbers and is denoted by wf on the closed interval. Oscillation of f on the closed interval ab. Oscillations of f on the closed interval ab. It is how it is defined: supremum of the absolute differences between f of t1 and f of t2, and t1 and t2 ranges over the closed interval ab. Okay, so how one can calculate this one? So in the literature results exist, and this is not in the form of theorem number 1. Okay, this is theorem, I am calling 1 or something. So this is proved. What is the oscillation of a function in the closed interval AB? It is nothing but supremum of f of t, where t belongs to closed interval AB, minus infimum of f of t, where t belongs to the closed interval AB. It is nothing but maximum of a function minus minimum of a function. This is nothing but oscillation. This is nothing but oscillation. In other words, we are going to sometimes, in the statistician people, they will call range. What is the range? Maximum value minus minimum value. So does this oscillation always exist? Because whenever f is continuous, if I am assuming f is continuous on a compact set, it is always have maximum value and minimum value. Because of the theorem, maximum minimum theorem. Okay, that the theorem I am going to use here for calculating oscillation of a function. So what are the bounds now? So here j is a natural number, means wavelets. J is in the equation I said na Vj equals to W naught, V naught plus W naught, that j here. And f is continuous. F is continuous on the closed interval AB. Okay, thank you. F is continuous, then its hard detail coefficients in equilibrium is djk. This djk satisfies the following inequalities. What is the first one? djk is mjk minus capital MJ, small mj, I will denote. So in the, what is the dyadic interval? K by 2 power j, k plus 1 by 2 power j. It is divided into two equal parts, midpoint, first half interval, second half interval. So capital M is the maximum of the throughout the interval, small m is the minimum of the throughout the interval, and single dash denotes the maximum minimum of f over the first half interval, double dash denotes the maximum minimum of f over the second half interval. So I will repeat one more time, this is just notation, that's all. Maximum value of f over the dyadic interval k by 2 power j, k plus 1 by 2 power j. Capital M stands for the maximum, small m stands for the minimum. Single dash stands for the maximum minimum of f over the first half interval, double dash denotes for the maximum of over the second half interval. Okay. So these are the inequalities, and we are going to prove in the next proof of this section. So these are all the notations I said. Single m dash means minimum of f, minimum is infimum. Okay. Because it is a continuous function, maximum can be replaced by supremum and infimum can be replaced by infimum or minimum, because you were considering in the compact subset. Okay. So these are the interval. Capital M double dash is the maximum or supremum over the second half interval. Small m double dash in front of the minimum of f over the second half interval. So these are all the proofs. Okay. In the proof, what are the important points? Okay, just like this is djk 2 power j. Yes, next previous slide. Yes, here I am going to use mean value theorem for definite integrals. Mean value theorem for definite integrals means integration of f over a closed interval AB, f of t dt can be written as f of c, where c is in the any point for some point in the closed interval. That theorem I have used here. Just mean value theorem for the definite integrals. So that theorem. Next, that is f of E1, f of E2. F of E1, E1 is in the first half interval, E2 is in the second half interval. Next, previous slide. Okay, next slide, sir. So now mod djk is equals to mod of f of E1 minus f of E2. E1 and E2 in the dyadic interval k by 2 power j, k plus 1 by 2 power j, and this is less than or equals to oscillation of a function. Because what is the oscillation? It is the supremum of mod of f of t1 minus f of t2, where t1 and t2 any 2 points in the closed interval AB. And E1 and E2 are at the particular points, therefore this absolute value is less than or equals to oscillation of a function. So this is the, okay, next, mod djk is less than or equals to wf, that is bar denotes for the compact subset, okay, because the oscillation will be can be understood over the compact subsets because of maximum minimum theorem. Okay. And further, these are all the integral. Whenever f is greater than or equals to g, then its integral is also greater than or equals to integral of g, and whenever f is less than or equals to g, its integral is also less than or equals to f of integral of f of is less than or integral of g. That I have used as result. Okay, next. Okay, this is the corollary. So what is the literature in the result? We are having only two bounds. One is related to Cauchy squares, we know another one is Majak bounds. He is assumed that f is differentiable. Okay, but in the theorem what we have written, it is just continuous. It's not necessary to assume differentiable. Okay, but I have to compare whatever derived bounds have to be compared with the literature. That is in the form of a corollary. Okay, suppose f is bounded and differentiable function, because Majak assumed that it is a bounded and differentiable function. Okay, then mod of f of t is mod f dash less than or equals to t for all t. Then mod of djk is less than or equals to the oscillation of a function, half of the oscillation. Further, this is less than or equals to eta divided by 2 power j plus 1. So whatever we have derived bounds is the sharper bounds compared to the Cauchy squares and next Majak bounds. Okay, these are the sharper bounds. Okay, this is the proof follows from the fact that eta divided by 2 power j plus 1 is the one of the upper bounds of the oscillation functions, because it is a supremum, it is a least upper bound. Okay, that's why it is which one? Oscillation of half of the oscillation is less than or equals to any of its upper bounds. Okay. Next, and the previous slide. So corollary 1 meets the goal of this presentation or article, because it is just copied from the article. Okay, what was our goal? Find the sharper bonds. We have reached our goal or not? So where the goal is reached in the form of a corollary. Okay, good. So now next I have to verify. So verify. So I have considered the 4 test examples, just 1 or 2 minutes. Okay, good. So now here I consider the e power x. It is just very friendly to everyone. E power x is a exponential function. F is, it is how much? E power x, and the interval is closed interval 0 1. So now I think are you able to distinguish the numer? I think it is okay, no problem. So anyway, corollary 1 meets our goal. That's all. Corollary 1 meets our goal. Oh, very good. Okay. Thank you. So just you point out one first row, it's sufficient. Okay. So these are the Cauchy squares bound. This is a Majak bound. This is derived bound. This is computed one. So actual value is minus 0.4208. Actual value is minus 0.4208. This is the size of the coefficient. If we consider the absolute, this is going to be 0.4208. According to Cauchy squares equality, we are estimating 0.4202 is less than or equals to 1.7873. In the case of Majak, this 0.4208 is less than or equals to 1.3591. But in case of what we have derived results, it is going to be 0.4208 is less than or equals to 0.8591. It is sharper bond. Okay, with these sharper bonds are obtained with the concept of oscillation of a function. Okay, this is good. So this is e power x, and you can compare all the other coefficients. Next, so this is here what kind of function I have. So these are very interesting examples. F of x equals to x into sine of 1 by x 0. So how many are here? Those who are present in the net set class workshop, please raise your hand. Yes. So I have used this function. Yes. Okay. So this is very important function. He is your one of good friend. He will always help you. He helped me to derive certain inequalities. So okay. But in the workshop we considered only f of x into sine 1 by x. But here I consider sine x into sine of 1 by x power 4. Why I have considered this one? Okay, what I said, Majak, what the Majak assumed? Continuous bounded differentiable function. Differentiable and bounded. Differentiable and bounded. But this function is differentiable. This function is differentiable. Yes. We said we have we solved this one in the workshop. What kind of function it is? Differentiable but not bounded. Why it is not bounded? You just apply the chain rule, multiplicative rule, x into cos product, x into cos of 1 by x power 4 into minus 4 divided by x cube. Yes? Am I sure? Minus 4 divided by x cube. ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ x cube x square ಬರುತ್ತೆ. Whenever x is close to 0, denominator will blast. Therefore it is unbounded. It is unbounded. Okay. So but Majak bounds cannot be help here to measure the R wavelet coefficients. But what we have derived method oscillations will always gives result. So Majak result is not which is not helpful to measure the R wavelet coefficients, because what is the hypothesis of his assumptions? Differentiable and bounded. Okay. Next. That's why one column is disappear compared to the previous table. Okay. Next. Okay. Okay. This is one kind of function, signum function. This is called 5 minutes. Okay. This is called signum function. Signum function is discontinuous. I have solved in the workshop also. Yes? Okay. Good. So how to measure the discontinuous? If you compute the R wavelet coefficient, wavelet coefficient will be large. Whenever R wavelet coefficient is large, then we can say that the function is not continuous in that region. In that region. See here. What is the R wavelet coefficient? D10 is minus 0.96, and all other R wavelet coefficients are close to 0. Okay, good. Next. So please zoom this to, okay. Yes. Compare these two diagrams. So this is the stem plot. This is called stem plot. So except only one value, all are close to 0. Except only one, all are close to 0. So it is having high magnitude. And that magnitude occurs at the certain point. It says that after computing the R wavelet coefficients, I am plotting stem plot. Only one coefficient is high compared to the other coefficients. What it says? Function is discontinuous at this point. Next. Okay. It says that it is continuous at this point, and it will also says that exactly at this point it is discontinuous. It also says exactly at this point continuous. Okay, discontinuous. Exactly at this point is discontinuous. If not point, it will give the small interval in which function is discontinuous. Okay, good. Next, this is the conclusion. What we have done? We have reached our goal and measured, derived sharper bounds, and we have applied those bounds. We have applied to test that given function is discontinuous or not at certain point. This is the application. Next. And what is the future work? Next slide. We will give the future work. What is the So whatever the functions I have considered, 4 test functions are very simple, and these are very simple in the context of mathematics, but in case of applications, they are nothing but noise and other. They are not simple as like our elementary functions. I have to implement this one to the real world problems applications in the future work. Okay. With this one, next slide. These are the references. Next. Thank you. Next, I am expecting questions so that it will give me a seed to the next conference organized by the Tumkur University, and I am going to Yes. If any question, I am ready to answer.
So students who are working in Weblet, they can ask question. So after listening sir's talk, definitely some doubt might have come
Yes.
or some.
I am using more properties of continuous functions on a compact set. That's all.
Hello, sir.
Hmm.
You introduce yourself.
Hello, sir. Myself Vidya Shah, research scholar.
Okay.
I have a doubt. Why we are using R wavelet only? There are many other wavelets
Yes,
also.
yes,
Chebyshev wavelet, Hermite wavelet,
Very good.
and some other wavelets. But you are using R wavelet
Yes,
only.
yes.
That one question arises in my mind.
Okay.
Another question is that if we can only solve in finite interval like in 0 to 1.
Yes.
This method is possible only in
Yes,
0 to 1.
yes.
If there is in negative interval, what we can do?
Okay.
I have this.
Two questions you are having.
Yes.
I will answer first question. What is my goal? I have to identify where is the discontinuity, but by Gibbs phenomena, otherwise Heisenberg concentration principle, it is not easy to point out at which function, at which point it is discontinuous. But we can identify very small interval such that that is going to be this interval containing a point of discontinuity. Small interval can be achieved only through R wavelets. Suppose if I am considering other than other wavelets, that compact support is going to be bigger. Yes, it will give the result. What it will give the result that in this interval it is having discontinuity. But we need what kind of interval?
Compact interval.
No, any wavelet will give the
Bounded.
compact, but
Size of the interval.
size of the interval must be
Small.
That can be achieved only through
R wavelet.
R wavelets.
Okay, sir.
That question
okay, sir.
clear?
I understand.
Next, so what do you mean by negative intervals? I am not understand. Give me one interval, negative interval. Okay.
Sir, in, for example, R wavelet itself, it is defined in the interval 0 to 1.
Okay.
And in other intervals, it is 0.
Yes.
If it is in, if the solution, if we want to find the solution in the negative intervals, like
Give me one negative interval.
minus 2 to minus 1,
Minus
minus 2 to minus 1,
minus 2 to minus 1.
Minus
Closed
one.
interval.
Closed
It is a
interval.
compact set.
Yes, sir.
All the properties of continuous functions can be applied on that one.
Yes, sir.
Yes or no?
Yes, sir.
Yes
You
or
can
no?
shift it,
Yes, you can shift.
Oh,
Shift or dilations.
Okay,
So what is it, and any closed interval AB is equivalent to closed interval 0 1.
yes, sir.
Then you shift to that one and study here. That's all.
Okay.
It's not necessary to consider only closed interval 0 1. Okay, because any closed interval AB is equivalent to the closed interval 0 1. You shift it and do the job, and because it's a bijective, and identify point in 0 1 and use the bijective map and locate the interval. That's all. Okay.
Thank you, sir.
Okay. Thank you. Any other question? Madam, only one person with two questions. But I
Actually, she
answer.
is working in wavelets.
Okay.
It's a PhD, so question arises on
It's no
in her
problem.
mind.
Okay.
But I think your goal is not fulfilled.
Yes. My expectations.
Expectation is
is
not
not-
fulfilled.
Okay, no problem.
So, on behalf of organizing committee, I would like to thank Professor Padmanabh Reddy sir. I would like to call upon Professor Sumitra ma'am to hand over the mementos as a token of gratitude.
Thank you, madam. Thank you for giving. I am very much thankful to the staff of the Department of Mathematics, Tumkur University. They are always inviting me to present in the workshop and the Tumkur. I am very much happy. Okay, thank you, madam. Thank you. Okay, thank you. Okay, thank you. Madam, thank you. 1 minute. Yes. Okay, no. Yes. Okay, thank you. Thank you, madam. Yes. Yes, sir. Okay.
Thank you, Sumitra ma'am. format.